My talk will be about some variant of the very classical problem, and I will try to convince you that this variant is worth looking into, just to learn something about the basic case. So the point of view I'm going to present is influenced by the many discussions with my colleagues Lech Dulek, Grzegorz Łutowski, and Dmitry Shabanov. Okay, let's start. So we are going to work with hypergraphs. And just to make notation shorter, K-uniform hypergraphs will be called K-graphs. Here is another example. We will deal with colorings, and first we color vertices, and the second thing is that today we work with only two colors. So this is one important difference between this talk and the previous one. We only are concerned with two colorings. So clearly the coloring is proper if there are not monochromatic edges. The other important difference will be that we think of K as being large. So you probably have seen many results of fixed K and number of vertices going to infinity, and then considering, for example, random hypergraphs. These are very interesting results. But for today, think of K as the basic parameter that goes to infinity. All right, so those two hypergraphs can be properly colored, but you can clearly see a missing edge in this example on the right. So if we add this just one edge, this example stops to be two colorable. So it's impossible to assign properly two colors. We are going to deal with this kind of problem. So given a number K, we are interested in what's the minimum number of edges in a K graph that is not two colorable. So the parameter was introduced by Erdős and Heinel a long time ago. And in the 60s, Erdős proved two results which gave the exponential rate of growth of this parameter. So we know that it grows like 2 to the k, but we just know a little bit more. So without any significant progress by 10 years, Erdős and Lovas suggested in the famous paper that maybe k times 2 to the k is the right order of magnitude, but this suggestion was not supported by any evidence. Or maybe it was a result of considering some special case of simple or linear hypergraphs. That was they considered in this paper. Okay, what we know today are those two results. So the lower bound improved a few times. The recent improvement was by Radhakrishnan and Srinivasan over 20 years ago, and we know that we have a lower bound like square root of k over log k times 2 to the k. The upper bound was not moved by a bit. I mean, we cannot improve this Erdős result from 64 even by reducing this constant here. Okay, just to give you a quick intuition about how this lower bound can be proved, it was proved originally by some application of Beck's random recoloring procedure, but you can rephrase it in many ways. So one nice way of rephrasing is that you color and you applying greedy coloring in a random order of vertices. And if you play with this, you will realize that you can determine some obstacles for this procedure. So you can convince yourself that whenever this procedure fails, there exists a configuration like this, that there is an edge that adds, whose last vertex is the first vertex of some other edge. So in fact, the analysis that gives this lower bound, it goes through probability of having no such configuration in a random permutation. And if there are no such permutation, then random greedy succeeds, and so on. Okay. The upper bound by Erdős, it was obtained by constructing a random hypergraph. So for carefully chosen number of vertices, he proves that if you're adding edges one by one, when you meet this number of edges, this constructed hypergraph is not two colorable almost surely. So this somehow indicates that random hypergraphs may be hard to color, but surprisingly, or maybe not, we can really improve a lower bound for random hypergraphs, and in many ways. So the first thing is that we can prove that this number obtained by Erdos is indeed a threshold for with proper parameterization of vertices, right? The number of vertices has to grow with k and roughly polynomial, let's say. And this number of edges is a threshold for two colorability. So it means that if you just take a fraction, any fraction close to one of this number of edges, the resulting hypergraph is very likely to be two colorable. So this is the first reason why the random graphs are not only hard but also easy. The second would be that you can do this in a constructive manner. We will get a weaker bound, but still much stronger than this lower. And the first result here would be that it can be even done for very weakly defined pseudo-random k-graphs. So if a graph that we observe, if it behaves in some specific sense like pseudo-random graphs, that some pretty straightforward procedure can improve over this lower bound. We will see an example of this kind of behavior later. All right, so before we move to the realm of non-uniform edges, so edges of different sizes, let us collect some information that is known about this specific case. So in general, the hypergraphs that we are dealing with are sparse. But among the sparse hypergraphs, some are more sparse than the others. So this notion of sparse and dense is relative. So if we try to determine which instances are hard and which are easy, so for which we can improve our lower bound, so one large family is the family of sparse hypergraphs. So the result is given by Lova's local lemma, so which gives local constraints. If the maximum edge of degree is not larger than this kind of value, then a hypergraph is too colorable. It means for us that if we take a hypergraph and it has a large number of edges, of vertices, I'm sorry, it has a large number of vertices, and this edges of these hypergraphs are somehow evenly distributed in a sense that degrees of vertices do not vary too much, then such instances are easy just because we can apply local lemma. So in order to for it to trigger, you would need like number of vertices, maybe like k cube or something like this. So it means that the hard instances cannot be too sparse. On the other hand, Radhakrishnan, Shanigrahi, and Venkat observed very interesting behavior. That when the number of vertices is too small, like k square over t, then again, when compared to the size of edges, right, to k, then again, this hypergraphs becomes easy. So to see that, let's take t like log like 8 times log k, right? Then this observation says that we can afford like k times 2 to the k edges in a hypergraph, and it's guaranteed to be too colorable. There is some byproduct. The resulting coloring from this observation is not only proper, it is also equitable or balanced in previous talk. You see they considered balanced coloring, and it is interesting behavior that we see quite often, that sometimes it's easier, it's technically easier to look for equitable coloring instead of just two coloring. All right, that means that if you want to determine what would be the pessimistic number of vertices in our hard instance of non-two colorable or two colorable graph, which is hard to color, for example, algorithmically, you should not go with the number of vertices below k squared. And in fact, this number of vertices used in the Erdős construction I mentioned was optimized exactly on the value of k² over 2 vertices. Okay, so we now move on to non-uniform hypergraphs. So we're trying to modify the problem, but keeping in mind that at some point we want to go back. So the results, my motivation for considering this result is to learn something about the basic notion. All right, non-uniform means that we can have many sizes of edges, but still we are going to work under some constraints. So let's say that a hypergraph in which edges are of size at least k will be called k+ graphs. Okay, we are going to formulate the analogous question to the previous of estimating the rate of growth of MFK. So in order to do it properly, let's define a random variable xh. It is just the number of monochromatic edges in the naive random coloring. Naive random coloring means that we're choosing the coloring uniformly at random. All right, we can discuss expected value of this random variable. It will be denoted by q of h, and clearly it can be expressed by this weighted sum of edges. And Erdős and Lovas in the paper from 75, they ask the following question. So we're considering k+ graphs, okay, and we want to have a function such that whenever the expected value of monochromatic edges is not too large, is bounded by this function, then the hypergraph is too colorable. Clearly, it is true for a constant function like 1. But the question was, how large function can you take? Or if in the first approximation, can the function be unbounded? It was answered like 3 years later by Beck. And he proved that indeed there exists such a function, and he used in his proof a very, very slowly growing function, roughly log star, yes, like iterated logarithm. And recently we managed to improve this bound to very slowly growing function, namely logarithm with some constants. Okay, what we learned from this consideration is the first thing was that it is worth to focus on hypergraphs with just 2 sizes of edges. So, and we have a strong feeling that if you can prove something for B-uniform hypergraphs, you can lift it up to the general case of all unconstrained size of edges. So a k prime graph is a hypergraph in which every edge has size either k or k prime. I assume that k is smaller than k prime, and edges of size k will be called short edges. Edges of size k prime will be called long edges. So we can precisely say what is the weakest link of our proof. So at some point, we considered a bunch of random variables, one for every long edge, and by some global events and other consideration, we managed to impose some constraints on distributions, very weak constraints, in fact. And we continue the proof by assuming the worst possible distribution that satisfied these constraints. So it is very clear that at that point, if we can do something better, so if we can control this distribution in a better way, then the lower bound will be improved. It is pretty much the similar situation that we meet at uniform case. So the same proof can be repeated in the uniform case, and you will see, and the weakest link will be in the very same place. So, for example, we can improve the lower bound whenever this random variable, number of monochromatic edges, is concentrated, right? And it works both in non-uniform and the uniform case. There must be some reason why in the uniform case we get better lower bound than in non-uniform, and here is the reason. It's pretty simple. I mean, in non-uniform case we worked with this kind of constraint, but in uniform it can be strengthened to this kind, just because that random variable xf is related to the number of vertices of long edge, and if the if H cannot have more than k vertices, so this gives much better bound, and it automatically translates to polynomial lower bounds, like square root of cubic root or something like this. All right. So if we focus on k and k prime graphs, it seems like a good question to ask what is the worst k prime that we can choose for a fixed k. So the theorem I mentioned before was that didn't make any difference. So it was saying that whatever k prime you choose, if the expectation is below log, you can two-color your hypergraph. But at the same time, you can expect that if your k prime is close to k, you can get something better, maybe close to the square root of k times log k. So you can do alternative proof to just trying to generalize this random greedy analysis in the case of non-uniform or b-uniform graphs, and you will get something that is sometimes better. Here's the picture. So it gets better as long as k prime is smaller than some function which grows like k log k. But past that point, it gets worse at what we obtain. And now if you think for a moment, it should be easy to improve these lower bounds once k prime is large again. So it is pretty easy to prove some better bound with logarithmic if k prime is exponential in k. We managed to get some bound for sub-exponential k prime, but weakly sub-exponential. But still, I think it's rather weak result. So the thing I imagine is worth considering is just focusing on some specific value a k prime, some polynomial in k, maybe k cube is a good starting point, and trying to improve this lower bound for this specific pair. I can show you what to expect in this regime. So let's start with k prime being of the order of k cube. And first thing we can consider is how many vertices should we put in our hypergraphs. So probably we should not take more than k prime square vertices, and maybe k prime square over 2 is a good choice, just like in the Erdős construction. Okay, now I want to take a look at the hypergraph of small edges. From the point of view of small edges, this number of vertices is very large. So just like before, if these small edges are evenly distributed over this set, we can expect that something is easy. And indeed, what we get immediately is that local lemma allows to eliminate all monochromatic short edges. It is not the end because we still have long edges to deal with, but it turns out that if we apply local lemma in a constructive, for example, in a constructive way, so we run a Moser-Tardos algorithm, it stops at some point at which there are no monochromatic short edges. And at that point, we have some coloring. This coloring is random. It is random in some sense. It is not uniformly random. That's pretty clear. But it turns out that it is random enough that you can continue with the somehow standard recoloring method to get rid of monochromatic long edges. Okay, so it means that this hypergraph of small edges cannot be evenly distributed, so it has to be somehow dense on some set of vertices. So there are 3 candidates for an interesting sets. So all these sets consist of the vertices with highest possible degrees in terms of this hypergraph of short edges. So let's take a look just of this largest one. Okay, and in a similar way, we can convince ourselves that in a pessimistic case, we should not observe any short edges outside of this square. Because, okay, previously we applied this Moser-Tardos procedure on the whole set of vertices, but now we can try to apply it on the fragment. It will give us some partial coloring, which is sufficiently random to continue with the rest of the hypergraph. So it's just this kind of edges just seem easy. Okay, so now we can imagine, or we can expect that lots of recoloring of short edges happens in this green square. So if you take a look at the log edges, it can either have small interaction, a small intersection with the square, and this is good because it means that somehow this recoloring of short edges have small influence on the colors of this long edge, and we can deal with this. On the other hand, if the long edge has large intersection in this within the square, we can apply this second dense argument. So I will remind you that if the number of vertices is small when compared to the square of the size of the edges, that equitable coloring allows to gain something. So for the sake of these edges, we should start coloring this green square not with random coloring, but with equitable coloring. And it will make this kind of edges easy. So what I wanted to show you is that if we deal with these KK prime graphs, we can try to observe some structure of the underlying graph. We can try to play with it and to prepare our tools for the general case. Okay, before I stop, it might be good to take a look at the upper bound, because if it's hard to, if the lower bounds are worse in the non-uniform case, that might be an indication that maybe the upper bound can be improved. And indeed, so I just recalled the upper bound, uniform upper bound by Erdős. So it is k squared times 2 to the k. Now this alpha is very specific constant. Think of this as specific constant. So in terms of Q, this weighted sum, it looks like alpha times k squared. And in case of non-uniform hypergraphs, we can improve it by a bit. So cutting this multiplicative factor by half. Construction is very simple, and in fact, it is B-uniform. So we start just like Erdős did. So we fix number of vertices k squared over 2, and we add edges one by one randomly up to the roughly this number of edges. So how of this number? Okay, at this point we stop. The hypergraph is still two colorable. It is very likely it is still two colorable, but it has relatively few proper coloring. And we continue with killing each proper coloring with a very large edge of size k prime, which is k squared over 4. And it turns out that the total mass, the total weight that we need to kill all the remaining colorings is very small when compared to this, to the mass of these original edges. So it shows that playing on this structure can bring some additional it can give us some hints about this pessimistic structure. It also shows that big uniform hypergraphs are in some sense strong. Okay, I think I will stop at this point and I will be glad to answer questions.
Let's say thank you to Jakub for his talk. Do we have any questions? I have a comment. I bet you tried to consider different non-uniform hypergraphs and possibly with several possible sizes of edges. So what kind of technical difficulties arises when we try to allow more sizes?
Well, you mean with 3 sizes?
For example.
No, I don't think there are important difficulties. I mean, at some point it boils down to proper weighting of edges. And I imagine that if you have a large span of sizes of edges, probably you can work with some approximation of the sizes. So probably if 2 sizes are close to each other, it doesn't make a difference that they are really different. So probably you can work with some gradation, like twice as large or maybe logarithmic k times log k and so on. So, and also I believe that there is some pessimistic quotient. So if you, there is really the worst k prime for k. So it would mean that in the end, I imagine that what you care about are only these pairs of sizes which realize this pessimistic quotient, and those that are outside of this are somehow easy cases or negligible. But it's just intuition or expectation.
Yeah, thank you.
I have a small comment. Recently, we considered co-function for the case B uniform hypergraphs, but not proper coloring, but for the case when we forbidden small black edges and big white edges. And in this case, co-function, I think, have another factor, not 2, but p and 1 minus p. And unfortunately, the upper bound on co-function is again square k. I don't know, maybe it is possible to improve square k, but
it seems hard to improve these upper ones. But in a case when you consider, I think what I understood from what you were saying, there is some connection between the hypergraph coloring and list coloring of bipartite hypergraphs. So, and at some point, just like you relax this this uniformity condition, you can think of bipartite hypergraphs in which lists on one side are short and with lists on other side are long. And it is not what I was talking about today. So this generalization on the side of hypergraphs, it goes in some other direction, but I think it's very close to the case I've heard just in the question. So maybe you should take a look at on these results.
Let's thank our speaker again.
Thank you very much.
Thank you.
Thank you, Jakub.